Okay, so we've gone through a lot of stuff in this class, right? So let's summarize what we've said. So we started with the concept of circuits. Now, what were circuits? Circuits are a special kind of electromagnetic components or apparatus that basically have a certain property. They are all much smaller than the wavelength of interest. We saw that if the dimensions of interest are much smaller than the wavelength of interest, then you're in the circuit domain. If they are much larger, you're looking at the classical or optics domain. And if they're comparable, you're in the microwave domain. Now, we saw in circuits, if you are in circuits domain, really what that meant is that there was really one assumption that you're making. You're making an assumption that the propagation happens instantaneously. In other words, you're assuming that the speed of light is infinity. And when you make that assumption, you will see that there's also no charge accumulation on any nodes. Now, when you have those two properties, you saw that you can create networks of elements attached to each other. And these networks, you could basically have certain rules governing these networks, which were the so-called KVL and KCL. Now, if you had a network of that sort, first of all, we also had another relationship. The number of branches was equal to the number of meshes, which are the window panes, plus the number of nodes minus 1. That was a basic property of the networks that we had. Now, within these networks, if we have the condition of dimensions being much smaller than the wavelength, or have the so-called lumped circuits, we had the KVL and KCL. Now, KVL and KCL were rules that basically describe, KCL said that the algebraic sum of all the currents leaving a node or entering a node is 0. For a given node. And KVL said the sum of the voltages around a loop, any loop in the circuit, a closed loop, is going to be 0. So there were different ways to apply these. And then we also saw that understanding the energy, the energetics of the things, the power delivered at any point, the instantaneous power, is the product of the voltage and the current. Now, we started with that, and then we came to the notion of the voltage and current. And when looking at the physics of the conductive material, we came up with this really empirical rule, which was the Ohm's law, that said that in a linear, so-called linear resistor, you have this relationship between the R and V. But in general, we know that V is R of I, is a function of I. And this is a nonlinear resistor. You can have nonlinear resistor, you can have time-varying resistor, you can have things that change, you can have memory, less memory. Well, memory resistor is kind of a funny thing, but most of the time, basically, the linearity or nonlinearity. And we saw an example of a nonlinear resistor, for example, was a diode, a p-n junction diode, that had a behavior like this. It's an exponential behavior. And we approximated that with an idealized diode, where the IV characteristic looked like that. So we saw that we could actually turn this really ideal diode into something less idealized by adding resistors and voltages. And when we did that, we could actually create curves that look like this. So you could actually create a threshold voltage and a slope that was determined by the resistor. If it's an IV curve, this would be 1 over R. So we had this linear resistors, we had the nonlinear resistors. And again, those rules, KVL and KCL, apply to all of them. We had the parallel combination, series combination, all that. Now, the next thing we did was that we said, yes, we could use these things and analyze things, but we came up with a more general way of thinking about networks and circuits. We came up with the nodal analysis. We said, if you have a network with n nodes, you could define one, or n plus 1 nodes. You can define one of the nodes as the reference potential, or the ground, and show the remaining nodes associated voltages V1, V2, and V3, and look at those, and have the nodal analysis. The nodal analysis consisted of several steps. The first one was to define the reference potential. The second one was to define these voltages with respect to these. And third one was to write KCL, the Kirchhoff current law, for these nodes in terms of node voltages. And the way you did that, for example, if you wanted to calculate this current, you wrote it as V2 minus V1 divided by this element, the resistance of that element, or times its conductance. And that produced a matrix, Y. that times the stimuli current Is vector produces the voltage vector, which no, the other way around. So the stimuli vector times the volt. So the stimuli vector is the Y matrix times times V, and that allowed you to calculate V by inverting that matrix and multiplying it by a stimuli. So this is basically a known, and this is the inverse matrix that allows you to calculate all the nodes voltages for a network. We also had a parallel, a dual analysis, which was the mesh analysis. We saw that you could actually define mesh currents, I1, I2, I3, and basically what we could do, we could write, for example, the KVL now using the mesh currents. For example, the voltage across this thing would be this element times this current minus that current, because that's a superposition of these two mesh currents. So, and that produced a different set of equations, which basically you had the Vs, the stimuli voltages, is Z matrix times I vector, which are the mesh currents. And to determine the mesh currents, you basically invert the Z matrix and multiply it by the vector Vs, the stimuli voltages. Now, a couple of important observations. The most important one is that this Z inverse is not this Y inverse is not this Z. They're not even the same size because they're not necessarily the same number of meshes as nodes and nodes in the circuits. The other thing to observe is that nodal analysis was more general because it allowed you to deal with non-planar circuits. Mesh analysis had the problem of having to be planar, so the currents actually couldn't cross each other, and we saw there are networks that are non-planar. And then mesh analysis would not be very useful for those. Now, the other thing that we saw is that when you invert the matrix, of course, the determinant of Y appears in the denominator. And that, if this determinant is 0, that's basically determines that's when the circuit becomes singular. And as we saw later on, is that those are the frequencies. The frequencies at which the root of this thing becomes 0 are the natural frequencies or the poles of the circuit. So you can determine the poles of a circuit by setting the determinant of Y of S to be 0. And that would generate all the frequencies that correspond to those, which basically would be all the four pole frequencies, the natural frequencies of the circuit. We also, the other thing that we did was that we looked at several theorems, the most important of which was the superposition. The superposition theorem allowed you to calculate the effect of different sources independently. The trick was that in a linear circuit, you basically null the remaining sources and you look at that. Now, we also talked about nulling a source. A nulling of a source was basically setting its value to 0. For a voltage source, nulling a source turns it into a short circuit. For a current source, it turns it into an open circuit. Now, we also had some other theorems. For example, we had the Thevenin and Norton equivalent. So if you had a network with various kinds of sources inside, dependent, independent sources, you saw that initially we saw it as a resistive one, but then even with capacitors and inductors, you could actually represent it as one voltage source and one impedance, Z of S in general, and a voltage V of T, or V of S, depending on which domain you're at. And this can be represented by that. So this is the Thevenin equivalent. And we also had the Norton equivalent, which basically said the same thing can be represented by some current source in parallel with the same impedance that you had here. Now, the way you determine this impedance is that you set all the independent sources, not the dependent sources, the independent sources to 0. You null all the independent sources only. And you look at the resistance seen, similar to the calculations that we had for example, the TTC, the time and transfer constant. And you look at that, and that impedance that you see is that Z of S. Now, the voltage that you see when this is open circuited is V of S, or V of T. And if you short circuit it, the current that passes would be I of S. So these were some of the basic theorems that we had. We had also the source transportation. We saw that if you had a voltage, for example, attached to something like this in a terminal, you can actually take that voltage and duplicate it here and get a Vs and Vs here, and this would be equivalent. We saw a similar thing for the current sources, source transportation. We had also source substitution, which is an important theorem. It says that if you, at some point in your network, if you have an element attached, and the voltage across this element, if you measure this voltage and see it to be V of t, you can replace this element inside that network with that exact V of t, with the exact dependence on time and frequency, etc., and replace it with a voltage source of that value. And nothing changes in the rest of the circuit. Essentially, the rest of the circuit has no way of knowing that something has changed because the voltage is the same. The same thing is true for its current. If you have an I of t here, you can also say this is equivalent. You can replace that element with an idealized or an ideal current source of that value. Right? So there were different things that we talked about on that front. Now, we also talked about active circuits in generality, particularly about op-amps. Now, with op-amps, what we saw is that if the op-amps are used in, let's go to a different whiteboard. Okay, so if you have an op-amp, we saw that it's really the model for this op-amp is an ideal. It models an idealized voltage amplifier. And you saw, one of the things that we saw is that if it is indeed in negative feedback configuration, if the feedback is negative, meaning that if when one side goes up, what happens is that the operation of the loop negates it, does the opposite. Now, if that's the case, we saw that there's some principle of asymptotic equality, which means that if the gain of op-amp is very large, this operation forces these two voltages to become asymptotically equal. So in other words, it assumes a value here, it just takes a value here that forces these to be equal. Because otherwise, what happens if the gain of this thing was going to infinity and these two were not equal, then you will have an infinite voltage at the output. So that's why this was useful in determining the transfer functions of op-amps and things of that sort. Now, then we started talking about inductors and capacitors. We talked about a capacitor being generally really a device whose Q was a function of its voltage, its charge. Now, if you remember, a resistor was an element whose current was a function of the voltage. Or you could say a voltage function of the current. But now we saw that if the charge is a function of the current, if you can draw a plot of Q versus V, now you have a capacitor. Now, if this plot is a linear one, you have a linear capacitor. If you have a nonlinear one, you have a nonlinear capacitor. Similarly, for an inductor, we saw that it's a device whose magnetic flux is a function of its current. And if it's a linear function, in other words, if it's an Li, this is a linear one, then its voltage, which is the derivative of this magnetic flux, is going to be L di dt. And similarly here, if you had a linear one, the slope of this thing was C, the capacitance, so it would be Q is equal CV. Therefore, I, which is dQ dt, becomes C dV dt. So those were some of the basic things that we talked about as far as the elements were concerned. The next thing we did was to come back and say, we started defining this, looking at the dynamics of the circuits. We started looking at the impulses, the Dirac deltas. We defined the Dirac delta initially with a pulse, but later on we saw that there are different ways of defining it. Perhaps with a sink would be even better to define it in that sense, but it doesn't matter really. The key property of a delta was the shifting property, meaning that the delta of x of tau, delta of t minus tau, d tau, when integrated from negative infinity to positive infinity, is going to be x of t, which we saw really, we thought about this as a lookup table for different values. We said we'd look at the value of that function at that point, we multiply by delta of t, and then scale it, put them next to each other. So we actually reconstruct the signal. It's a way of reconstructing the signal as a sum of a large number of deltas with different heights, proportional to its actual value at that point. And then we use this to determine the response of the system. Now, before we did that, we saw some basic properties of the delta. For example, we saw that u of t, the unit step function, was simply the integral of the delta of t. And we had this notation of p. The operator p was defined as the derivative with respect to time, and 1 over p was defined as the integration from negative infinity to t of a function dt. So once you have these two, then you can look at it this way, or you can define the delta of t as p u of t. We also saw that we had other singularity functions. You could continue beyond this point. You could define the ramp of t, the ramp function, as, which you can also write as tu of t, as 1 over p of u of t, which is basically 1 over p squared of delta of t, and so on and so forth. It's the second integration of that. Now, one of the most important results that we got in this course, and one of the key results really, was that if you have a system with an input x of t and an output y of t, you could evaluate, and this, if this system were an LTI system, you could evaluate its, you could assess and determine its properties completely by knowing its impulse response, h of t. And the way we did that, we actually used that sifting property and applied the operation on it. And we saw that y of t, in fact, was x of t convolved with h of t, which is written as the integral from negative infinity to positive infinity of x of tau, h of t minus tau, d tau. Now, if the system was linear, but not time invariant, in other words, linear but time varying, you could still use a similar integration, which is basically the superposition integral. But now h of t, h would be functions of t and tau, not just their time difference. So in that case, y of t would be x of tau, h of t and tau, d tau. So it's a catalog of impulse responses. For different times, you have different impulse responses because your system is time varying. It's not time invariant. So that's basically what you get in a linear system. Now, we saw the convolution is an operation. So convolution in particular was quite important, and we saw that it was a flip and slide operation. So you flip one of the waveforms and slide it across the other one, and you look at the product of the two, and then you calculate that product and evaluate it for different values of t. So that's how we performed convolution of two functions, right? And we've seen many examples of that through this course. Now, then we saw that the response of a circuit really consists of two things. You can break it down into different parts. You can write a response as the sum of the natural response and the forced response. The natural response of the system is basically the way the system behaves in the absence of an outside stimulus. And the forced response is what it does in the absence of any of its own, basically when it's dominated by the forced input to it. We could also write this in a different way. We could also write it as the sum of the steady state response and the transient response. So there are two different ways of writing this. Now, we saw that for a first order system, if you know it's a first order system, if you have, for example, a single capacitor or a single inductor in the system, the response of the system, the time domain response, let's say a voltage at some point, could be written in the following form. You could write it as v of infinity plus v of 0 plus minus v of infinity times e to the negative t over tau, the whole thing times u of t. And this was a way to determine responses, for example, for those switch circuits. If you have things that are switched, for every time you have to find the initial value right after the transition, because that transition can have an instantaneous change in the system, depending on how it is. It may instantaneously change the value. So that's why you're looking at v of 0 plus. And then you look at its value at infinite time and use that to determine its overall time domain response. Now, then the next thing we did, so let's move to a different whiteboard. So the other things that we did was that we said, okay, now if you have this capacitors and inductors in the circuits, you could define this impedance and admittance operators. So we took the P and 1 over P operator, and we extended it. We said, look, you can define a voltage across something as the operator Z of P operating on its current as a function of time. Or conversely, its current being the operator Y of P operating on its voltage. Now, one of the things that enabled us to use these operators extensively was when we found what the inverse operator associated with 1 over P plus A is, right? And that corresponded to the case when you had a first order differential equation of this form. If you had a first order differential equation of this form, you could write it as P plus A operating on Y of T producing X of T. And therefore, Y of T would be the inverse operator, which we started showing it this way, and we saw that it made sense to show it this way because they behaved like rational polynomials operating on X of T. And then one of the things that enabled us to do a lot of stuff was basically to determine what this operator was. We determined what this operator was as e to the negative at 1 over P e to the at x of t, which you can write in a longer form if you want to write the actual, spell out the integral as this. Right? So this is what we did with that. And then we use this low-pass operator. This was what we call the low-pass operator to determine the response of the system to a variety of different things. Then we saw that in general, if you have an nth order system, which corresponds to an nth order differential equation with like coefficients such as bn y nth derivative plus bn minus 1 y to the n minus 1 nth derivative all the way to the b1 y prime plus b0 y being equal to am y x to the mth derivative of x all the way to a1 the first derivative a0 x. If you have something like this, you could write it in terms of the p operator with a polynomial, characteristic polynomial, which was basically bn p to the n, bn minus 1 p to the n minus 1 all the way down to b1 p plus b0 all operating on y. And on this side also you could write as am p to the m all the way to a1p plus a0 operating on x. And from this you could see that y of t could be determined by this operator, this rational operator operating on x of t. And then we saw different ways of doing this, which we saw you could try to factor this into smaller elements, but we saw that if you actually use partial fraction expansion in complex numbers, we could express this as the sum of terms that look like that, which was called the partial fraction expansion. So when we did the partial fraction expansion of this thing, and of course first we have to make sure that the order of this is less than that. If it is more than that, then you do a long division first and then you do that. But at the end of the day, you have basically something that looks like this. You can write it as, I don't know, p plus r1 p plus r2 all the way. You may have multiple roots. We learned how to deal with those too. Rn operating on y of t producing x of t. But now we saw the power of this thing was that when you did something like this, it allowed you to individually look at these responses. And once we knew what the time domain response of these things was, we didn't even need to calculate this integral anymore. We went to the catalog, and once we reduced it to the sum of these elements that were in the catalog, and there were certain rules to use that catalog, we actually could produce the response of a system completely from that, which is very powerful. It's essentially a way of solving nth order differential equations completely. And again, as I said, we use complex numbers. The rules of complex numbers, essentially the most important one is that e to the j theta is written as cosine of theta plus j sine of theta. So we use that for calculations. We also dealt with second order systems in particular. There was some certain terminology for second order system which was quite helpful. You could write it as 1 plus 1 over q p over omega n plus p squared over omega n squared, and this was the natural frequency and this was the quality factor, so we could write them this way, and that allowed us to know what the properties and the transfer functions of these things are in terms of q and all that. Now the next step we did, which is basically a part of this, was that the other thing that enabled us was to define not only the systems but also the inputs and outputs in terms using the operator. And how we did that? We took advantage of delta. So we defined not only the system, the transfer functions, h of p's, but also x of p's and y of p's. And we defined x of p's and y of p's as operators that generated the desired signal off of a delta, a Dirac delta. And once we generate them off of that, we saw that there's no need for doing the individual dealing with those and dealing with the delta anyway. So the key result was really that when you had a system with an x of t input and y of t output with an impulse response h of t, you could also look at the x of p, capital X of p, capital Y of p, these two operators, the input operators and the output operator, and the system operator, h of p, which is the one that corresponds to the h of t, and we had a key result, which was that y of p was h of p times y of p, which corresponded to the time domain relation of h of t in h being y of t being h of t convolved with, oh, this should be x of p, x of t. So the key result here was that the convolution in time domain corresponded to a multiplication in the operator domain, which we saw later on, which was basically the complex frequency domain. Now, we took that, and then we also saw that we could also look at the response of a system to an e to the st input, e to the negative st, and that led us to the Laplace transform. So the Laplace transform of h of t was defined as h of t e to the negative st dt. Doesn't really have to be prime. Which we show it with capital H of s. And what the Laplace transform really was the response of a system to an e to the st, e to the negative st input. Right? Now, what it really is that it was a special case of applying the operator. So the operator system didn't really need to have those kind of machinery and it was a more general machinery, and it didn't have to really worry that much about the regions of convergence and all those things. But with Laplace transform, you do. And we saw that there was almost a one-to-one correspondence between the catalog that we created for the operator and the catalog that we created for the Laplace transform. So we went through that pretty rapidly. And the key result here is that we saw that the system function was essentially the Laplace transform of the impulse response. So this is the system function, which can correspond to the system operator if you replace an s with a p, and this is just the impulse response. Okay? So that was that. And then from there, we said that, okay, yes, Laplace transform is nice, and then we looked at several different things. We looked at, for example, the response of the system when you had poles and zeros. We defined the roots. If you had a transfer function h of s, and you had roots of the numerator and roots of the denominator, we called the roots of the numerator zeros of the system, and the roots of the denominator, the poles of the system. And we saw that we show zeros with the circle on the S-plane. So this is the sigma j omega plane, S-plane, complex plane. And then we saw that, and we demonstrated that for system to be stable, meaning that its impulse response being eventually decaying to 0, you need to have poles on the left half plane. Now, you can have zeros on the left half plane or right half plane, that's fine. Both they don't result in a negative, in an unstable system, but it takes one pole on the right half side to make the system unstable. And we had these poles and zero constellations that we looked at. And we also saw what the response of the time domain response of the system for each one of them looked like. So if your system just had this pole on the left half plane, we saw that the impulse response would be some sort of an exponential decay. And we saw that if you had a pair of complex conjugate poles, we saw that it was a decaying, an exponentially decaying cosine and sine. If you had a pair of poles on the j omega axis, the response would be non-decaying sinusoid. And if you had a pole on this side, it would basically correspond to an exponentially growing one. If you had a pole here, it was an exponentially growing, simple exponential growth. This would be the pair of complex conjugate ones correspond to an exponentially growing sine or cosine. We've gone over all of this before. That's why we are going. Now, we also saw that there was a criterion for what, there are many criteria. We haven't talked about all of them. The simplest one for determining if the system is stable or not, if you're given a polynomial, was the Routh-Horvitz method, which was basically you took every other coefficient and you wrote them in two rows, and then you did this basically cross multiplication and division by the term that was closest to you. You wrote them down. If there was a change of sign, for every change of sign of the first column, you basically had one right half plane pole. It doesn't tell you anything about the zeros, really. Now, then we took this and we took it to the, so one of the interesting things that we did is that we said, okay, look, if you have a cascade of systems, meaning the output of the first one is the input to the second one, and so on and so forth, then we saw that, of course, the overall impulse response is the convolution of the three impulse responses. But more interestingly, and probably in a more useful fashion generally, is that the transfer function of the overall system is the product of these transfer functions. Now, that brought us to something that was a more special case of this, which was basically said, look, what happens to the sinusoidal, purely sinusoidal perturbations? What's the forced response for purely sinusoidal systems? And in that case, we basically we created the phasor notation, where basically we represented a sine and cosine by a vector representing its magnitude and its phase. Right? So you have the magnitude and the phase of the system. You could have basically the amplitude and the phase, if you will. And we used those to determine this. So in other words, we looked at S being equal to j omega. We looked at it under a special case when you're looking at the j omega axis. And we perturbed the system, and that led us to the Bode plots. So we said that Bode plots was a way of plotting these things. And it was useful because being a logarithmic representation of the magnitude, it allowed us to convert this multiplication to a summation. And the Bode plots that we created looked kind of like this. So for example, you had 20 log of the magnitude of h of j omega and the angle of h of j omega. This being logarithmic and this being linear results in being able to add the Bode plots associated with the system in cascade to produce the overall response of the system. And we saw that there were rules for determining the Bode plot, or showing the Bode plot. For example, if you had a left half plane pole at a certain frequency, we saw that there were two asymptotes associated with that. So this would be a left half plane pole, and the phase associated with the left half plane pole started dropping, and it went from 0 to negative 90 degrees. At this point, it was at negative 45 degrees. Now, we also saw that we could actually go, and if you had a left half plane 0, so if you had a left half plane 0, what happens is that this goes up and this goes up. Now, the interesting thing to pay attention to is that right half-plane poles and right half-plane zeros particularly are doing certain things the same way and certain things differently. So a right half-plane zero would have a similar amplitude, but its phase behaves like a phase of a left half-plane pole. So its amplitude is the same whether it's left half-plane or right half-plane, but its phase switches when it's left half-plane versus right half-plane. And the same thing is true about right half-plane pole. The magnitude part of it would behave this way, but its phase behavior is like that of a left half-plane zero. So that's for that. And then what else did we do? So we looked at those. We also saw that if there's a second order system, there would be peaking. So there would be the amount of peaking is proportional to the quality factor. So if you have a second order system, you will have peaking, and this would be roughly Q happening at omega n. And we took that and used it. So now the last thing we did was basically looking at the Fourier transform. We took the Laplace transform and we looked at it on the j omega axis, or conversely, we took the Fourier series, which allows you to write a periodic waveform as a sum of exponentials or cosines and sines, and convert that to a series of sines and cosines. So you could, in general, write it as e to the j 2 pi n f naught t, for n being from going from negative infinity to positive infinity. And we saw that eventually that corresponded to the Laplace, to the Fourier transform. The Fourier transform being x of f, capital X of f, being defined as the integral from negative infinity to positive infinity of x of t e to the negative j 2 pi n f naught t dt. And the beauty of the Fourier transform was that it allowed you to perform the inverse, which was essentially the same operation with a minus sign difference, which gives you x of f e to the j 2 pi n f0 t df. So you had a pair of transforms that allowed you to go back and forth. And we saw that this basically being the inverse transform, you saw that the convolution in time domain, as we expected from the Laplace and operator domain, would correspond to a multiplication in frequency domain. And conversely, the multiplication in frequency domain, in time domain, corresponded to a convolution in the frequency domain, which allowed us to play all sorts of games, which we saw examples of in modulation and sampling and dealing with those. So that was kind of like a very super fast review of what we covered in this class. Again, it misses a lot of details. So any questions? Yes? Say again? Oh, there's no n, sorry. There's no n. Yes, the n is it's supposed to be an error. Okay, any other questions? Okay, well, let's go.